Welcome to the exercises of lesson 3. First question, which is not given in the answer set, is exercise 3.5. So we have a set with the elements 1, this one, with the element 0, with the set with elements 0, 1, 2, and with the set of element 2. First question, what is the number of elements of the set A? Well, I've just listed them. So the element 1, the element 0, the element is set with elements 0, 1, 2, and the set with element 2. So the number is 4. Okay, next question. So is the set with element 0, so you have to really carefully read the question, is the set with element 0, is that an element of A? And then the answer is no. Don't fall for this trick question, eh? So 0 itself is an element of A, but not the set with element 0 inside. Okay, then we have a question about a subset. So are the elements 0 and 1 part of A? So is the set with the element 0, 1 a subset of A? Means that we have to check whether the elements inside that set, so that 0 and 1, are elements of A. And then the answer is yes, because 1, 0 is both an element of A. Okay, is the set 0 with elements 0, 1, 2 a subset of A? And then the answer again is no, because this element here, 2, is not part of A. We have a set with element 2, but not the element 2 itself. So no. Last question, and this is a difficult one, because then we still have to remember what was this PA. Well, that meant the power set of A. So PA are all the sets we can make with elements of A. So, for instance, I can make the set with element 1, or the set with element 0, or the set, and now it becomes difficult, with as element the set 0, 1, 2. That's quite different than from those single elements, etc. Well, already you recognize that this one here, the set with element 1 inside, is an element of the power set. So the answer is yes. Question 3.6. We have two sets, and the first question is how many elements does the power set of A contain? Well, the power set of A contains all possible subsets you can make with the elements of the original set, and hopefully you remember that that is 2 to the power of the number of elements of the set A. In this case, A has 5 elements, so it's 2 to the power of 5. B, give the intersection of the power set of A and the power set of B. So how many subsets we can make with the elements A are also doable with the elements of B. Okay, then we have to look for similarities. So we see the element 2 there in both sets, and we have the element 6 in both sets. And don't forget that the empty set is always part of any power set. So let's start with that one, so we will not forget that one. Okay, then I can make a subset from A with only the element 2, which I can also make from B. So this one is in the intersection. And of course, with the simple element 6, it's also possible. But then we also can make a subset with a combination. So 2, 6. And that'll do the trick. So the complete intersection are the elements 0, empty set, set with 2, set with 6, and set with 2, 6. Okay, then the questions with the propositional part. So we have a proposition P, I get hungry, Q, I eat, R, I become fat, and then the sentence which we'll have to write with the help of P, Q, and R. If I become fat, so that's R, then, so if then, that's an implication, I don't eat. So I do not eat, not Q. Don't worry what it means, huh? Just translate that. Don't try to think about it. Question B. I get fat if and only if, so I get fat, that is R. If and only if, that's the by implication. Then there is a compound statement. I eat and I don't get hungry. So I eat Q and I do not get hungry, not P. Question C. If I get hungry and I eat, so this is again a compound one, then I don't become fat. So I get hungry and I eat, so that's P and Q. Then an if then, so an implication, I don't become fat, not R. Question 311. Show by using the logical laws that the two propositions are equivalent. Okay, so we have to reason from this one and from that one and to show that they are equivalent. So let's just start with the left one. P implies Q or P implies R. Okay, that is equivalent with. So we have to simplify this implication, the switcheroo law. And P implies Q is equivalent with not P or Q. And then just put down that you're using the switcheroo law. Okay, or, and then the same thing applies. P implies R is equivalent with not P or R. Okay, this is nice because I only have ors, so I can use associative law. Now just drop every bracket, and I can also, let's do that in one blow, just switch them around because of the commutative law. So I'll put the nots together, not P or not P or Q or R. Okay, then we have not P or not P. We can put them together. Idempotent law. So that gives us not P or Q or R. Okay, we can't make it any simpler. I've just cleaned it up a little bit and I've just left the conclusion which we reached at the end of the last part. So now we're going to start from the right. So let's give it a different color. So the right part, not Q and not R, implies not P. Okay, what shall we do first? Well, we have the implication again, so let's use the switcheroo law. So that's equivalent with the first part negated, so that's not Q and not R. Or, and then the second part stays, not P. Well, then we have a not with some brackets and an and, so then we can use De Morgan. So that means that we will put the not inside the brackets. So not Q, and let's change that immediately in Q. The and flips, becomes a or, and the not R becomes R, or not P. Now it looks already very elegant. We can use associative law to drop all the brackets. So that means Q or R or not P. Okay, and let's make it completely the same by using commutative law. So we'll put the not P in front, then the Q, then the R. And you see, we have a perfect match. So indeed, the left proposition is equivalent with the right proposition. So thanks for watching the video, and next video we'll continue with the exercises of lesson 4.